Okay, let's start. Good morning. Before we our class, I'd like to have a brief um, discussion about our middle term exam. Um, I guess uh, many people not satisfied with their result, right? And I talked to a few students. They really concerned how to learn this course well, and then I think middle term exam is a good mirror uh, for us to check, to self-check where we didn't do well. Right? And I look at the problem is, you see, if you look at our, we have four problems. The first problem, all just very basic concepts. So I call first principle, right? Some first principle some first principle, I should say, is a grandmother, right? The grandpa first principle, let's say Maxwell equations, right? That cannot be wrong. And also, you you'll have chance to write it down in your information sheet. So I don't think that is easy. And another kind of first principle, for example, boundary condition, right? What is the basic property of the electromagnetic field across a boundary of between two media? And also this is very clearly stated in class, so we should know, right? And if you look at the problem 4, and that is the problem maybe our students feel most difficult. I don't understand why it is difficult. We had similar examples discussed in class. We have one question in assignment. It's almost the same, right? The only difference is coefficient. One is 2, one is 3, right? And this maybe what worried me is, do our students really do our assignment, right? Do you do assignment by yourself? Do you go back to check, okay, what first principle you use in conducting that assignment, right? And I keep emphasize, right? I keep emphasize we should learn first principle and how to use first principle to solve problems. And I keep encouraging our students, you say, do assignment by yourself, right? And you must do it. If you have any difficulty, and we have a very good resource, we have 4 very professional tutors, okay? And also, you can come talk to me, right? We can make arrangement, you say, to answer a question either after class, okay, or just make another time we can discuss over Zoom, right? I'm very happy to talk to our students. Okay, I'm not a tiger, right? And then also you don't need to worry I will bite you. And so we're in a far distance, right? Okay, right now it's not too late. Okay, not too late to catch up. Right? And some of the basic concept we will repeat from now on until final exam, right? And then I will also gave assignment that involve a basic concept and also some of the concepts you need to solve using first principle to practice, okay? And don't be hesitate, talk to TA or talk to me, all right? Okay. So now let's start a new chapter. This chapter, you see the title still plane waves, but the difference is now we are, from now on, we are going to discuss the interaction of electromagnetic wave, or specifically Planck wave, okay, to an object, okay, the interaction. So this object could be something like a wall, big wall, right? If we talk about electromagnetic wave directly, or later on you will see how electromagnetic wave propagate in high frequency circuit, we call RF, radio frequency, or microwave circuit, right? And the description is a property, the electromagnetic wave down the transmission line and in free space, you will find out amazingly the same. Okay, they're the same, right? So when we discuss the basic property of electromagnetic wave in free space, that result equations, formulas, okay, the basic concept is the same. When we deal with electromagnetic wave down the circuit, even down a very, very tiny high frequency, radio frequency, or microwave integrated circuit, the behavior is the same, right? So we don't need to discuss one by one repeat. We just talk about how wave propagate in free space, the basic concept. Then we will use that concept in different fields, right? We know how to use that. Okay, so from this chapter, we emphasize interactions, okay? And what we have done in the last chapter is, right, we talk about how the wave is generated, right? And then we give you a very tiny electric current dipole antenna, right? So if you have a current, we assume the current is constant uniform current, okay? Then that can generate electromagnetic wave. We can analytically analyze it, right? We find what is the behavior in the near region, and also what is the behavior in the far distance, right? And then we justify when the electromagnetic wave propagate in the far distance, what is the properties? The property exactly the same as we introduce a Planck wave, right? So the Planck wave means we have electrical field polarization or vector electrical field. We have a magnetic field has another polarization direction, which is perpendicular to electrical field. Both electrical field and magnetic field perpendicular to the direction of propagation. All right. Okay. So that is the basic property of Planck wave. Oh, by the way, we also have a property is electrical field divided by magnetic field equal to a constant. What's that constant called? We call intrinsic wave impedance, right? So that is a constant we can calculate by hand. That is approximately equal to 120 pi, right? Okay, that is what we have learned. You see how the wave is generated. Okay, now we're not surprised where the wave has been generated, right? And then let's see how we can make use of the wave. Okay, for example, we make use of the wave for radar. Okay, this is a radar. Okay, what the radar is for detection of you say the flying object, right? It's either for civilian use or for military use, right? You say in every airport, you can see a very sophisticated radar system because they need to check how many airplanes planes in the sky is going to be landed, right? From different direction, what the distance is, right? And for military use, you see, by all means, right, to detect, you see, the enemy, the flight. And one way we can use, you see, radar to detect the object in a long distance, very, very far away in the, even in 1,000 kilometers, okay? Then we also need to take into account the curvature, okay? The curvature of the Earth, right? The curvature of the Earth. Then people use radar to send plane wave hit on the ionosphere layer. So this layer is highly conductive, high conductivity. Okay, this is a highly ionized atom. Okay, you can treat it like a very good conductor. And then this is about 30 miles high. And also the thickness is also about 30 miles. Okay, so it's very high conductive layers. Then the electromagnetic wave can hit on the layer, get reflection. Okay, the Earth also tend to be a good conductor, particularly if this is sea waters. Okay, the salt water is also very highly conductive, right? Then you have reflect again. So we have a multiple reflection, right? Then this multiple reflection allow us to see a plane which your eye never can see, right? Even blocked by the curvature of the Earth, right? So radar can still see it, right? And when we design very advanced radar, we need to design very advanced antenna array. This antenna array has a beam that can steal the beam, right? And also the antenna array can create multiple beams of electromagnetic wave. We call the beam, let's say, if we use a polar coordinate, okay, then we can have a beam. That means we have a very a high field strength in one direction. We can have another beam point to the other direction, okay, point to other direction, so and so on. So, for example, you see the radar on the ship, okay, like a carrier. So they can track tens of objects in the same time, right? Okay, so that is application radar, right? And also we have application. We send electromagnetic wave through a cable, RF cable, radio frequency cable. Okay, if you still remember the problem 3 in our middle term, we have one question. We have one question is electromagnetic wave give you electrical field, give you magnetic field. Okay, down this coaxial cable and let you to find the average power, right? And the pointing vector, right? So that is a typical electromagnetic wave, but it's a propagation not in open space, is in a confined region, right? So that is a way people send electromagnetic wave for long distance. And by all means, you see the fiber optics is also very typical application of electromagnetic wave, right? By the way, you see, you all know who is Professor Charles Cobb, right? he's a microwave engineer. Okay. He was a microwave engineer when he worked in this standard lab in UK, and then at that time, every company is working on how to transmit electromagnetic wave of wideband signal for a long distance. Okay, so that gave him a chance to invent fiber optic. Right. All right, so that is a very basic background, right? Okay, now let's have a brief review. Okay, brief review plane wave, right? We said electromagnetic wave is a vector. You must have a polarization. How to describe polarization? We use a vector. Okay. For example, this is example. Okay. The example means the wave polarized in x direction. But wave can polarize in any direction, right? Don't make a mistake is white horse is a horse and the black horse is not horse. Okay. Or the horse must be white. This is wrong. Okay. This is not correct. Okay. I give you example is the this electric field polarized in x direction does not mean only can polarize in x direction. Or how do you define x direction? It's defined by you. If you call this is x direction, this is x direction. If you call this is x direction, this is also x direction. It's up to you, right? So that basically, for convenience, we call x direction, right? Then since why mention y, you know, if this is x, y must be perpendicular to x, right? Because you learned this in elementary school. So I don't need to repeat this again. That's the only reason I call x, right? And then I know if this is x, this is y, this is z. Okay, I don't need to repeat this. So that's why I call x, okay? Then if you can write in x, then you can write in any component, okay? Then for plane wave, if electric field in x direction, magnetic field in y direction, then we can find the solution, okay? In phasor, okay? Because everything we talk about phasor. Because phasor, first we eliminate time variables, okay? Because time variable is reflect in j omega t. This is the time convention, okay? We don't need to repeat this, but we put in our heart, right? So for plane wave, we have a solution because this is the x component, okay? This is x component, right? Or if you like say electric field in vector, then I can say x. This is also fine, right? But this is x component. Now, sometimes I like to emphasize this is a phasor. So I put a bar. I put a bar. Okay, I put a bar. Okay, this bar I emphasize this is a phasor, but you don't have to write. If you know clearly this is a phasor. Okay, so this is a phasor, right? We have wave propagate in positive z direction, propagate in minus z direction, right? So this is a very specific form for phasor. In general, if we are not talking about phasor, we have proved we can have arbitrary function. That function must have an argument, okay, in this form. Or we have another function, okay, the argument is in this form, okay. So v is wave velocity, right? But this is a g and f can be any function, right? But for time harmonic, field, Okay, then this can be cosine omega t plus any initial phase, okay, then minus beta z, okay? So this is a specific function for G, right? You can write this is another for F, this become omega t. You can have another initial phase, but this is plus beta z, okay? So this is a, we just review this, okay? So when we look at exponential function, gamma is a propagation constant. Gamma is a propagation constant, which involve, this is attenuation factor, this is a phase constant, right? Okay, then we have discussed this in a lot of details, so we don't repeat. And once we know electrical field through Maxwell equations, this is a Maxwell equations. Okay, this is Maxwell equations. We can find analytically what a magnetic field is. Please pay attention, okay? When we have, this is a wave propagating in positive direction, we have a component for magnetic field propagating in positive direction, okay? Then we have wave term propagating in minus z direction. We also have a term magnetic field propagating minus z direction. But for magnetic field propagating in minus direction, we have a minus sign, okay? We have a minus sign here, right? But the ratio either between positive z direction or between negative z direction, the ratio is the same, which is wave impedance, okay? This wave impedance for lossy media, is a complex number we have to write in this way, right? We also introduce phasor expression and instantaneous expression, right? What is the relation? What is the relation? Once we know phasor, this is a phasor, okay? If we want to convert into time domain, instantaneous expression, right? Then by following the first principle, this is the first principle. So some of us still don't understand. Professor, you always keep mentioning first principle. What is first principle? See, any laws, definitely first principle. This is proven to be true unless you can prove it is not true, right? Second, definition. You cannot be more basic than definition, right? This is the definition. Okay, this is definition. How we define the phasor? Phasor is defined like by this. Okay, in all our discussion, phasor is defined by this term multiply our time convention. You take a real part is your real field. This is the real. Okay, and measurable. Okay, is a measurable. Real number or even real field. Real field, because you can measure, right? Real quantity. Real world quantity. Okay, is that clear? Real world quantity. But phasor is a mathematical quantity, is complex. Okay, is imaginary quantity or not real quantity. Okay, but however, very convenient. To use. Okay, very convenient to use. So this is, we introduce phasor only for convenience, only for convenience. Okay, right? If you say for Poynting vector, if you say this is a okay, this is T, right? Vector cross E cross H. Okay, but however, in phasor, we justify. Okay, this is a function of frequency. So we justify yesterday. This is complex conjugate, right? So for Poynting vector, right? For Poynting vector. So phasor is only for convenience, right? But when you deal with a lossy medium, particularly when you deal with a lossy medium, phasor is a great convenience. Okay. Even I can say without using phasor, I don't know how to handle it using pencil and paper. Okay. Very, very difficult. Maybe this one formula we derive, we need to take a couple pages to derive it. If I didn't use phasor, right? You see, for example, how we deal with lossy media. If we know electrical field, how we find magnetic field, right? We had this problem in middle term exam, but we need to use this concept all the time. By the way, you see the final exam doesn't cover the material we already covered in middle term. But however, the concept, the basic concept we learned before middle term, definitely we will use in the second part of our course, right? Okay, definitely we need to use. See, once we know electrical field, how to find the magnetic field, right? So we just divide. This is wave impedance. Because wave impedance is a complex number. When we mention complex numbers, that means you are using phasor. Because real world quantity is, you never can find complex number. Right? Okay. So when you use complex number, this is a phasor. So we divide wave impedance in both. We propagate in positive z direction and negative z direction factor, right? So once we involve this complex number, we have a phase. This is a phase. Phase is not phasor, it's a phase, right? Any complex number you can write in terms of magnitude and phase, right? So we put this phase into this exponential function, then we take a real part, you see? Then we take a real part. This is everything become real number when you convert into instantaneous expression. All right. Okay. So we finish a brief review of plane wave. Okay. And this part I'm going to introduce later on. So now let's talk about our real business. Our real business is we have infinitely large wall, conducting wall. Okay, this conductivity goes to infinity. We call perfect conductor. Okay, this is a perfect conductor. This is a perfect conductor. Then this wall divides this space into two, right? One we call medium one. In medium one, I assume there are no loss. Okay. Sigma 1 equal to 0. And the other side is a medium 2. Okay, so conductivity goes to infinity. Okay, once we go infinity, that means electromagnetic wave cannot exist in conductor. We gave example, right? If electromagnetic wave can penetrate into conductor, that will be in a very, very shallow surface or very, very small distance measured in terms of micron, right? And we call that shallow surface or skin, right? We call that is a skin. And we can calculate the depth or thickness of the skin. We call skin depth, okay? We discussed this already. We don't repeat this, right? Because if we always repeat, we have no time to learn new things. Now, this is our situation. Now, what we are going to do is we have a plane wave propagating in that direction. This is that direction. The propagating in that direction. Okay, then this is x. This is x. Okay, let me highlight x. That. Okay. Now we have wave propagating in that direction. I assume electrical field polarize in x direction. I can polarize in any direction, but we treat, you see, I can treat the wave. You may ask me, why, Professor Wu, why you not discuss the wave polarize in this direction? Yes, we can discuss this. But if I polarize in this direction, the propagating direction must be in this direction, right? If I call this is called K. Because electrical field must be perpendicular to propagation direction. This situation is a little bit more difficult. Okay, let's put this at the very end. Okay, at the very end. Now let's say we discuss a scenario. We discuss a scenario is the wave perpendicularly hit on the wall, right? And the electrical field must polarize in the direction perpendicular to a propagation direction. That means electrical field is in parallel with the wall, right? If it is in parallel, okay, if this is a wall, if this is parallel, so any rotation is a parallel, right? But because this wall is infinitely large, doesn't matter what direction I call it is x. I hope you are not mine, okay? Okay. Okay, you don't mind, right? I polarize in x direction. Then how to describe it? A plane wave propagating in positive z direction, polarizing in x direction. Look, okay. This unit vector means describing the polarization direction, right? This is the polarization direction, right? This is a polarization direction. Then how to describe propagating in that direction and the positive z direction minus beta z. Beta is the propagation constant, right? Because we're talking about beta, right? We're talking about beta, right? The propagation constant. and minus that means propagating in that direction. Let me repeat, why is minus z? Because don't forget, if I have a minus j beta z, don't forget we have a time convention, then I can write it like j omega t minus beta z, right? Okay, so this is phase. If I keep phase is a constant, if this is constant, one time increase, if I keep a phase constant, what z should be? Z must be constant. Z must be increased too, right? So that means to keep the constant phase, one with time goes, the wave propagates in positive z direction. Okay. The other way around, if this is a positive, with time goes, if I want to keep constant, the z must be decreased, right? That means propagating minus z direction. Okay, I think I explained this many times. All right, so don't forget, okay, we also gave arbitrary magnitude. Arbitrary magnitude. The arbitrary magnitude, there could be 1, could be 100, could be 1,000. So I don't know. You see, that depends on your transmitter, how much power you transmitted, and also depend on the distance you travel. Okay. Many people, when you describe plane wave in this way, do you have any questions about this? You see, when we derive our plane wave, we said that in the far field, so that is a proportional to this, not that, let's say r, right? Inversely proportional to r, and then even though you have a magnitude. Now you say, Professor Wu, you said, oh, plane wave becomes this. Then where this r goes? Okay, where this r goes? Not r, 1 over r goes. This 1 over r, if I call this is a 1 constant, okay, then if you don't mind, I call this is original constant that depends on how much power you transmit, divided by z. Do you mind? Because this r, now we know how wave is transmitted. This is antenna. Okay, this r is in the far field. Okay, this is 1 over r. Okay. See, this is 1,000 meter, right? So if you talk about 1,000 meter and 1,010 meter, if you talk about 1,000 meter and another is 1,010 meter, what a difference? There's not much difference. Okay, there's not much difference, right? So that's why when we talk about the plane wave, to simplify it, to make our life easier, okay, we have this approximation, then this r is already involved into this constant, okay, into this constant. So that means this constant is also determined by how far this r is 1,000 meter or 10,000 meter, right? Right? We can say the electromagnetic wave can propagate in tens of kilometers, not just measure in meter, right? So That's why you say we deal with this simplified form, okay, not this the actual solution form, okay, and with a very, very little difference, which is you cannot distinguish, because when we deal with this interaction, the distance, okay, between your observation point and the object is not very far, right? Okay, now let's continue. We have electrical field fully described, plane wave, fully described. Okay, by, so that means we must have three important factors, right? First, polarization. The second, phase turn, right? Third, you have a magnitude. Even though we don't know what's in magnitude, but we have something, okay? We have something, the magnitude. If you write plane wave with all these three factors, you won't be wrong, okay? You won't be wrong, right? Okay, now once we have, sorry, this is electrical field, okay, propagation direction. Once we have electrical field, we also need to find magnetic field. Talking about the plane wave, if we know the propagation direction, if we know electrical field, if we know the wave impedance, piece of cake, right? Piece of cake is just divided by wave impedance. If you treat magnetic field as current, if you treat electrical field as a voltage, like a voltage, then the current is a voltage divided by resistance, the Ohm's law, right? So this is a resistance, this is a voltage, this is the current. Easy to remember, right? For plane wave. Okay, question is, we need to find the correct resistance or impedance. If this is lossy media, this impedance is a complex number. All right, okay. Now we get ready. We get ready to say the interaction. Now we have electrical field, we have a magnetic field. We call this wave is coming, is incident wave. Indicated by I, okay? I means incident wave, okay? So this incident wave coming EX, HY, in that direction, okay? Now hit on the wall. Then let's see what happened, okay? Hit on the wall. What will happen? We can imagine, oh, we will have a reflection, right? Because anything wave hit on an object always have a reflection, right? Including acoustic wave, right? If we talk to the wall, sure, you must have a big wall. The wall must have a very good reflection. Then you can hear the echo, right? Right? So I don't know, have you ever surveyed the 九龙壁在北京天坛呢 right? So you have a wall that create acre for you, right? Right, okay. Now we expect we have a reflected wave, okay? Once we have incident wave, we expect to have a reflected wave, okay? But now we don't know what is the solution form of reflected wave. We need to find out, okay? So I don't know what is the magnitude, okay? But let's do one thing at a time. We have three things for plane wave. For plane waves, okay? Then three things. First, polarization, right? Now let's see, for reflected wave, what is the polarization for reflected wave? When the wave is a normal incident on the wall, what is the polarization direction? I don't know, okay? At this moment, I don't know, but let me take a guess, okay? Let me take a guess. Very likely is polarized in the same direction. Okay, let's take a guess. If we can justify it is correct, then we take it. If we couldn't justify that, then let's change, right? So now let's see, first is polarizing x direction. Polarizing x direction. Sorry, I have to take 4 minutes more, all right? First, I assume this is polarized in the same direction. Okay. Second, let's write a phase term. Okay. This phase term, because it's a propagate reflected wave, right, must propagate in minus z direction. So I must have a positive sign. You agree, right? Okay, positive sign. And the positive sign z. Okay. And also because the reflected wave propagate in the same medium, that means the wave constant, the propagation constant, the beta, should be the same as incident wave because they travel in the same direction, okay? Same medium, right? So same beta. So I also using the beta 1. So I answered the second part. Okay, the second thing. And the third thing is the magnitude, right? But this magnitude, I don't know, okay? I don't know. Let's find out. Let's find out. But let's put it as unknown first. Okay, it's unknown, right? Let's consider if we can find it or not. Okay, if we can find it or not. We need to take a little bit longer. Okay, let's take a break. Then let's take a break for now. Let's resume at 10:30. Okay, so let's resume. Okay, now we mathematically describe the incident wave and the reflected wave, right? Incident wave and the reflected waves in medium 1, and then we can imagine the total field. Okay, the total electrical field. The total electrical field in medium 1 will be a linear superposed by incident wave and the reflected wave, right? We have incident wave, we have a reflected wave, so the total field add together, right? Total field add together. Then total field add together, we have incident field, polarizing x direction, we know the magnitude, and then the phase constant, don't forget it is a minus g, okay? And the plus reflected wave, magnitude, I don't know, okay? But however, the propagation constant, I know, okay? This is plus. We add together, this is the total field. So we have a total field E1, okay? In medium 1. Of course, we have total field E2 in perfect conductor, which is 0, right? Or constant equal to 0, right? So this equal to 0. Then we know what we know the boundary condition. What we know is the property of electromagnetic field on the conductor. Electromagnetic field on the conductor, the total field on the conductor is 0. Okay. The boundary condition of electrical field on the surface of, we should say, tangential. The tangential electrical field, its conducting surface is 0, right? What do you mean tangential component? Because our total field only exists polarized in x direction. The polarization direction is the tangential direction of the boundary, x, right? So that means the total field in medium 1, the coordinates z equal to 0, which means on the boundary, right? That should be equal to 0, okay? Then I substitute z equal to 0, z equal to 0, right? Then we have this, the magnitude of the incident wave plus magnitude of reflected wave equal to 0. This is a condition. This is a boundary condition. This is a condition derived from boundary condition, right? The boundary condition is the first principle, okay? That tangential field, the tangential field on the boundary equal to 0, right? This is first principle, right? So therefore, this equal to 0 or this cannot be wrong, okay? If you, every step, you follow the first principle, your result cannot be wrong, right? All right, so that what that means is, even though I don't know the magnitude of incident wave, even though I don't know exactly value, but I know this can be measured, right? Can be measured, okay? But I don't mind what that is. This relation is always true. What that means is the magnitude for reflected wave equal to minus of magnitude of incident wave, right? Then we substitute this relation into the, general expression of incident wave plus reflected wave, okay? Then we come to this, right? All right, and this, if you know trigonometry function related to the exponential function, that equal to this. That is a total field in medium 1. Okay, total field in medium 1. Now we get the solution. The polarization direction in x direction. This assumption works. Okay, the reflected wave polarizing in x direction, it works. Okay, so that means our initial guess is correct. Okay, so we don't need to find another possibility, right? So this solution exists. Here you see we use a simple relation is a sine equal to this, right? And then with a minus sign, okay, and 2j, right, with 2j. So this is high school stuff. Now, once we know the electrical field, we also need to know magnetic field. Okay, so to obtain the magnetic field, for reflected wave, we already know, right? We already know is the direction, the polarization direction for magnetic field is the propagation direction cross multiply the electric field propagate in minus that direction, or R, right? So in this case, the unit direction for reflected wave is a minus Z. All right, and the direction for electrical field, reflected wave electrical field, in what direction? In minus, that is a minus X direction, right? The wave is propagated in minus X direction. You see? Oh, sorry. I shouldn't call this. This is total field. This is a reflected wave. The reflected wave is in minus AX. Okay, then EI0 and J beta Z. Okay, so this is in minus, reflected wave is in minus AX, minus X direction, right? So let's look at our coordinate system. It's defined like this, right? X, Y, Z. Now, a reflected wave is in minus Z direction. This is A and R, right? So this direction minus cross minus Z cross minus X in Y direction. In Y direction, right? In Y direction. So this is a direction in Y direction. Okay, this is in Y direction. And then this is the magnitude of voltage divided by impedance. Okay, then phase constant. This is how we can write the magnetic, how we can find the magnetic field for reflected wave. Okay, for reflected wave. So once we know reflected wave for magnetic field, we also know the incident wave for magnetic field, right? We have, did we write incident? Oh, sorry, we didn't write incident wave. Incident wave for magnetic field. Incident wave for magnetic field is 1x. This is incident. Okay, polarized in X direction, and the magnetic field also in Y direction. So this is polarized in Y direction. The incident wave magnitude divided by wave impedance in medium 1. Okay, then the phase is beta 1 times Z. Okay, this is incident magnetic field. Okay, then reflected wave magnetic field also in Y direction. All right, then its magnitude also divided by the same thing. Okay, then right. So this is total field for magnetic field. So what that means is this equal to, okay, then we have all right. Okay, so I divide by 2, I multiply by 2, right? So this term equal to cosine beta Z, right? right? So this is how we obtain this. Okay, this is the magnetic field. Okay, this is magnetic field, the total magnetic field. Now, pay attention. Okay, I said electrical field divided by magnetic field. I don't know what is your polarization direction. Okay, this equal to wave impedance. I said this is in analogous to voltage divided by current equal to R, right? Okay, this only applicable to either incident wave or reflected wave. It does not applicable to the total field. Can you see this? If this is applicable to total field, what that means is, you see, but this is either incident or reflect. Okay, not total field. If total field, that would be wrong, right? Okay, if you take a total field, then you see, I know Professor Wu said H field is easy, right? The total field, you have polarized X direction, then I just copy this field, then divided by this. This is a magnetic field. This is a completely wrong. Completely wrong. I never said this is applicable to total field. So that would be stranger, right? How to apply this? Okay. How to apply this for the stranger field? Okay. In what case we can apply this rule is, let's define a concept we call the concept. Let's define concept. One is called traveling wave. One is called standing wave. Okay, these two terminologies are very useful. Okay, very useful. The traveling wave, travel, right? We know what travel means, right? Traveling means for pleasure, right? And then you travel from one place to another place, right? You travel, right? So this is a traveling wave. That means traveling wave never come back. You travel from one point to another point. Okay, so that means if you describe the wave by exponential function, only wave propagate in one direction, the wave only propagate in one direction is the phasor expression is a traveling wave. This is the first principle. Okay, this is a definition, right? This is a traveling wave, right? This is a traveling wave. Traveling wave travel in that direction. This is traveling wave travel in minus that direction. This is electrical field. This is also traveling wave. Okay. So for traveling wave, Ohm's law is applicable. Okay. For traveling wave, Ohm's law is applicable. Right? You see, the current can be voltage divided by resistance or impedance. Okay, this is traveling wave. What is a standing wave? Standing wave is when you have two waves superposed together. Okay, superposed together. Then we will look at the functions. behavior. Okay, it forms they form traveling standing wave. Okay, see, we have incident wave, we have a reflected wave propagated in that direction and minus that direction. All right. Okay. So this is traveling wave, right? Oh, sorry. This is a standing wave. This is a form standing wave. For standing wave, we cannot apply. Okay. For standing wave, we cannot do that. For traveling wave, we can do this. Okay, we can do this, right? You see, when we superpose two traveling waves, you can apply Ohm's law to each traveling wave. Okay, to each traveling wave, then add together to form a new standing wave. That is magnetic field. Okay, that is magnetic field. So this, you cannot apply Ohm's law to the total field, to the standing wave directly. Okay, you only can apply to traveling wave. Right. Now let's look at this function. Okay, what is the behavior? What is the behavior of this? The behavior, we found the total electrical field. We find the total magnetic field. All right. Then let's observe this wave back into real world quantity, which is instantaneous expression in time domain, right? In time domain. To convert this is a phasor, this is a phasor. Okay? This is a phasor. Then we multiply the phasor by Ej omega t. Okay. Right? I said this is a 酒肉穿肠过，佛祖留心中, right? Okay, so this is something the God we always keep in our mind, right? Okay, so this time convention, even though we don't need to repeatedly write it down each time when we manipulate the phasor, but it exists. Okay, it defined in field quantity. Okay, remember, if you give a power, can you do this? Say, sure, you said the pointing vector is E cross H conjugate. Okay, can you find the P in instantaneous expression? Also take this. Can we do this? No. No. Because our definition, we never mention this is applied to power. We only defined in field quantity. Okay? Electrical field, magnetic field, field quantity. If you want to find this, okay, you must find this E field first. This is a phasor, then dot, this is correct. Okay, this is correct, right? Okay, this is side note, right? Now let's convert electrical field into its instantaneous expression. Okay, which is straightforward, right? Okay, we have this is magnitude, and then don't forget, because we have a J, we have a j, right? We have a j. So once we multiply this quantity by e j omega t, okay, so this is a cosine, or you can say this is cosine omega t plus j sine omega t, right? Okay, so don't forget we have a j, right? So that means we take a sine omega t, right? So this is a simple complex number, and then we don't waste time here. And similarly, we can find the magnetic field, okay? Because magnetic field, we don't have j, right? We don't have j here, so we use cosine omega t. Now, this is the field expression. Sorry, the pattern, E field and H field, and the boundary always equal to 0, right? Always equal to 0. So if we fix a time omega t, okay. So let's take a snapshot. Let's take a snapshot at a different t or different omega t, right? If your omega t equal to 0, so this is always 0, right? So that means the magnitude change, right? At a certain time instant, omega t equal to 0. What do you say? Everywhere in the space, you don't have field. If omega t change, okay, omega t increase, okay, then you say the total magnitude increase until omega t equal to pi over 2. Okay, omega t equal to pi over 2, you get the maximum value. All right. Okay, pi over 2, you get maximum value. Okay, and also this pi over 2, then always minus pi over 2. This, you change the sign, right? So it depends on where you located for giving that distance, right? If you located here, you'll see the maximum change, right? At a different time. If you happen the beta z for giving beta, if you happen to locate here, the beta z equal to pi over 2, right? If beta z equal to pi over 2, no. If beta z equal to pi, okay? Sorry, this is that. If beta z equal to pi, okay? So that means this is always equal to 0. So minus pi, because z 0 is here, right? So here is everything is a minus, right? So everything is a minus that. So if beta z equal to minus pi, this point, this constant equal to 0. So you cannot measure any electrical field, right? If happens that if beta z equal to minus pi over 2, so that means you're standing here. This is a beta z equal to minus pi over 2, right? So you can experience the maximum change of the field. So that means depending on where you are, or depending on what time instant you take a snapshot, the pattern is 2 sine function multiplication. All right, either one factor depends on the location. One, it depends on the location. One depends on the time. One depends on the time. So this is a 2 factors. Okay, 2 factors. So for sure is some location you never can find field. Okay, you never can measure the field, such as here, right? And then some place you can find the maximum change field, but however, it's not always constant value, right? So it's change with time up and down. You see, sometimes it's there, sometimes it goes to the maximum time, maximum positive value, sometimes negative value, and then go back to zero, and go back to maximum, and go back to zero, and go back to negative, right? So this is a sinusoidally change very fast because omega is high. Such a wave we call standing wave, okay? Such type of wave we call standing wave. Okay, so this is a standing wave. This is standing wave. And similarly, for magnetic field, the behavior is the same, but not at a different location, not the same value as the electrical field. Not the same value. Okay, for magnetic field, tangential magnetic field, it happens when electrical field equal to zero, magnetic field reaches to maximum, right? You see, because when z equal to zero, cosine beta z equal to maximum value 1, right? Okay, then when the electrical field at this location, you can experience the largest magnetic field or largest electrical field. Then the same location in magnetic field, you detect zero. You won't measure any magnetic field in certain location, in this particular location, right? But when the location you cannot measure electrical field, then you can find the maximum magnetic field in the same location. So that's why you see sometimes people build antenna, two kinds of antenna put together. One is to measure electrical field, one is to measure magnetic field, right? So that means if you couldn't detect electrical field, then you may have a high chance to detect magnetic field. So this is what we call diversity antenna, okay? Diversity antenna. So this is the observation for the field pattern. And also some important observation, okay? If we can measure the distance between two zeros or distance between two maximum or the distance between any equal magnitude strength, what you can do, this distance, we can use this distance to measure the wavelength, because this distance is half wavelength. We can use this measured wavelength, we can predict what is the frequency for the wave, right? What is the frequency for the wave? So this is very useful information. Very useful information, right? It depends on what point is more convenient for you to measure. Okay, you can more convenient, you can measure, if you convenient to measure the zero location, you can measure zero. Or if you think you can measure the largest, the highest value, is also possible, right? Okay. Let's make a summary. Let's make a summary. Once the electromagnetic wave hit on a conducting wall, I emphasize we perpendicular hit on the conducting wall, right? We perpendicularly hit on the conducting wall. We can form a pure standing wave. We like to call this is called the pure standing wave. Why it is a pure standing wave? Later on, you will appreciate. If this is not pure, okay. So pure is mean you can find 0 point, okay. Some location you can find 0 point, okay. So this is pure. Then the behavior for standing wave is different from traveling wave. By the way, if say for traveling wave, let's say this is a traveling wave, right? Let's say so with that, the incident wave is a traveling wave. It's a traveling wave. I omit the polarization direction. Okay, this is constant. This is a minus j beta 1. That this is a traveling wave. Look at the magnitude. Does this magnitude change with distance? This magnitude is a constant. Do you agree? It's sure, because this is a complex number. This is a complex number. This is a complex number. But however, this is independent to distance. No matter what, at what distance, you measure the magnitude is constant. This is for traveling wave. For traveling wave. Okay, for traveling wave. But for standing wave, I don't repeat, right? For standing wave, if you take a magnitude, okay, not including the polarization direction, right? If you look at the magnitude, of course, you see, we already see here, right? We already see here, the magnitude is a function of a location. This is a very distinct identity, okay, to distinguish traveling wave and standing wave, okay. Right, okay, we have 10 minutes to briefly let's talk about, so that can save us some time tomorrow. Or not tomorrow. Now let's take a look another scenario. Okay, let's take a look of another scenario. Another half of space is not a conductor anymore. Okay, another half space is a medium 2. This medium 2, we have conductivity, but not very high. Or let's assume this is 0. Okay, so this is also 0. Let's talk about lossless case. Okay. This is a lossless case. Okay. If this is a lossless case, and also plane wave normal incident hit on this interface to see what happened. Okay. This interaction, let's see what will happen. Again, we assume our incident wave for electric field polarized in X direction again. Magnetic field, I use Ohm's law here. Okay, I call Ohm's law, but nobody call it Ohm's law in electromagnetic field except me. Okay, I think it's easier for us to remember. Okay, the relation with wave impedance. That's it. Okay, nobody call this is Ohm's law. It's just I just help us to remember this relation. Okay, this is I can apply this Ohm's law. Okay, Ohm's law again, right? I can apply this Ohm's law because this is a traveling wave. Okay, traveling wave. I can apply Ohm's law. So this is incident electric field, incident magnetic field. Again, I assume reflected wave. Okay, I assume a reflected wave also polarized in the same direction as the incident wave, and the magnitude I don't know. Okay. By the same token, I can write the magnetic field, reflected wave. Reflected wave propagating only in one direction, which is minus that direction, which is a traveling wave. I can apply Ohm's law again, right? Okay, then this relation, somebody asked this relation. This relation is the propagation direction. Okay, this is the propagation direction multiply the electrical field that determine then divided by wave impedance. This is electrical field. Okay, this is a general relation. This is general relation. Okay, this is the general relation concluded from the special case we had discussed. But you can check, go back to check our discussion, right? You can find this is always true. So we use this relation to find magnetic field. Okay, we can find the magnetic field. Then I can use Ohm's law because reflected magnetic field also traveling wave propagating in single direction. Okay, minus that direction. Now we have incident wave, we have a reflected wave mathematic description. Now we need to determine the relation between the magnitude of incident wave, magnitude of reflected wave. We need to find, and also because this is dielectric, while we expecting the reflected wave, we also expect some of the wave propagate into other half space. Okay, into other half space. We call such wave, we call transmitted wave. Okay, we call transmitted wave. The other wave, we call transmitted wave. So this transmitted wave propagating in that direction because other half is infinitely large. So when this propagating in that direction, they never come back because there's not any obstacle. Let it come back. In our situation, okay, then we let it travel, never come back. So this is also traveling wave. Do you agree? We also assume polarized in the same direction as incident wave. Okay. Now we don't know the magnitude. Okay. Sure, we have another relation for transmitted wave. What is the magnitude? So we need to find the relations between them. Between these three things. All right. How to find this basic relation between them? How to find the basic relation between them? Okay. How to find? We said no matter how complex or how simple electromagnetic wave problem is, okay, two things you need to satisfy. If you satisfy these two things, you get the work. Two things is, one is must satisfy Maxwell equations. Second is must satisfy the boundary conditions. Only these two things. Okay. Now, satisfy the Maxwell equations is already guaranteed because this solution form, this traveling wave solution form, is a solution of Maxwell equations. We did together, right? We did together. If you don't recall, go back to check. Okay, we did together this solution form. No matter is reflected wave, no matter is reflected wave or incident wave all satisfy maximum equations. Okay, we answered the first question. The second question is boundary condition, right? We studied what the basic property of the boundary condition is. Now it's time to apply it. Okay, now is the time to apply boundary condition to find the relationship. To find the relationship, okay, using boundary condition. Okay, find a relationship using boundary condition to find the relationships. Okay, now let's see how to apply. Oh, by the way, pay attention. You see, in medium 1, I use beta 1. In medium 2, because constitutive parameters, permittivity and permeability is different. Beta will be different, right? Beta will be different. Okay, now I use beta 2. Beta 2. Now let's see how to find the relation, how to apply boundary condition. First of all, let's find the total field. The total field for electrical field, the total field in region 1 is EI plus ER, right? This is arbitrary Z. Okay, then the total field in medium 2, so this is EI plus ER. Then medium 2, we only have a transmit wave. Okay, so now we have incident wave and the reflected wave. This is the total field. Let's apply this two total field on the boundary. Again, we look at the tangential field component. Tangential field component must equal for electrical field. Okay, must equal for electrical field. And for magnetic field, if we don't have a current sheet, on the common boundary, the tangential magnetic field also should be continuous, equal. So I apply tangential field, electrical field equal, tangential field, magnetic field equal. Why apply this? You said Z equal to 0, so this equal to 1, this equal to 1, this equal to 1, right? Same component, so you have this, right? Similarly, for magnetic field, if you set this equal to 1, this equal to 1, this equal to 1, okay? You get this relation. Now it's good time to solve this. Two equations, we have 3 unknowns, right? But I don't like to call we have 3 unknowns. We only have 2 unknowns because the incident, this suppose is known. Suppose is known, right? Because this is decided by, I said, by traveling distance, R, decided by your transmitter, the power you transmitted, okay? Okay, this is known. So suppose then we have 2 unknowns, which is, we have 2 unknowns. One is reflect wave, one is a transmit wave, right? Reflect wave, transmit wave. We have 2 equations, 2 unknowns. Then we can find out what the relation. Okay, this is we call reflect wave, transmit wave, all with respect to incident wave. Okay, because incident wave is known, right? I call this ratio I call this ratio, I call reflection coefficient. I call reflection coefficient. You see, because reflected wave magnitude divided by incident wave magnitude. This is how I measure how much energy reflect, right? With respect to incident wave. I call this equal reflection coefficient. Anybody don't feel comfortable, right? Same as I measure the transmitter wave in terms of incident wave. I call transmission coefficient. Okay, I call this transmission coefficient. And also, very easily from the first equation, we can find they're related. Okay, they're related. Incident wave, transmitter wave, reflective coefficient, transmission coefficient related by this. Okay. Now it's time to stop here. Now, may I ask you to derive this simple relation by yourself from these two equations? Okay, this is one of homework. Okay, this is one of the homeworks this week. Okay, I still keep posting homework. If you want to get good mark, you must do homework assignment by yourself, and then you have to do it, and then you need to do it. I greatly help you. If you have difficulties, and talk to TA, or you can talk to me, right? Okay, so all right, so let's stop here today. So I'll be stay here, and if you like to ask me some questions, welcome. Right? Okay. See you next week. Don't forget your high count.